Stopped last time. We were talking about analog to digital conversion. So just a second. Yeah. Yes. So we are talking about analog to digital conversion. The first question is, how are analog and digital signals different, and how do I believe we have answered the question that why do we need analog to digital conversion in detail last time. So I won't be going into that again, but let's first answer how are analog and digital signals different. So start. Tell me, how are analog and digital signals different?
Sir, analog systems take values from
Signals.
take value uh, on a continuous set, and digital signals take values on a countable or discrete set.
Okay, so analog signals take value from a set take from the set false. Not any discrete set, but specifically this binary set 0, 1 or true false. See, digital signals, you should be able to apply all the digital operations on them. And for digital operations, any discrete set won't work, right?
Okay, sir.
Yes. So it has to be this set. So this 1, 2.
The bandwidth of digital should be higher because since it's
Bandwidth
like
is
because it takes discrete values, so it needs more number of like that signs to get that value.
let's not go into the bandwidth. There's a
Okay.
simpler difference that these can exist, or these are defined for all values of time. These defined in terms of sequences and hence only at fixed discrete. Fine. See, digital signals always are always defined as sequences.
So can't there be continuous value, continuous time discrete, digital signals? Like we, like the one, or say like the clock signals that we get.
Clock signals. So those clock signals are actually analog signals. They are not digital signals.
Okay.
Those are actually, so any practical signal. Here's a key mistake that everyone makes, and even I used to make until quite late in my career, that any signal that can be sent over a physical medium is an analog signal. We live in an analog world. All the digital signals are abstract ideas that are made realizable. Like I said this earlier as well, digital electronics. All the digital logic is made possible via certain physical analog circuits. The circuits, the physical signals are always analog.
Okay, sir.
All the digital circuits contain analog components. We view them as from a layer of abstraction, or we view those components as black boxes that enable us to implement digital logic. So this is actually the biggest difference. Exist physically are abstract. Because if you talk about your digital circuits lab again, what you called a 0 was actually 0 volts or minus 5 volts. What you called a 1 was actually 5 volts. Continuous wave. So these are just abstract ideas that are so in general, analog to digital conversion is conversion of a continuous time, continuous valued signal fine. The process of analog to digital conversion is basically this. So the question is, so the steps. It's popularly known as sampling. converting the samples from continuous or converting the valued samples to discrete quantization. Mapping the so these are the 3 steps involved in analog to digital conversion. Fine. So we'll just write these down as a block diagram. So I send in xt, sampling, I get xn, quantization, I get x hat n. This what is x hat n? We'll make this clear when we reach this point. And binary. Fine. So the question is, or the question are the mathematical details of these processes: sampling, quantization, and encoding. So we'll start with the first process, sampling. So consider an energy signal GT with Fourier transform GF that needs to be converted to a discrete time signal such that the signal GT can be recovered from the resulting discrete time signal. Fine. So the process of sampling is that I take a continuous time energy signal and I want to convert it to a discrete time signal such that the true signal can be recovered from the samples. Sounds fair enough? Any problems with this?
No, sir.
Yeah. So you have done sampling in signal
Yes,
systems?
sir. In signals and systems.
Okay, cool. So I'll spend a lot less time over here then. So you would know the Nyquist sampling theorem.
Yes, sir.
Cool. Have you done flat top sampling and natural sampling?
No, sir.
No, sir.
Okay. So let's just run through sampling then. And then we'll do flat top sampling, natural sampling, and obviously you wouldn't have talked about sampling random processes because this is the first time
No, sir.
we have talked about random processes.
Yes, sir.
Yeah, so our agenda for this discussion is then sampling, ideal sampling. So what you have done till now is what we call ideal sampling. That let GT be uniformly sampled using train of pulses PT equals summation n goes from minus infinity to infinity delta t minus ts. Fine. So this is basically a comb, you can say, that has pulses at every NTS. Now sample sequence of GT sample sequence of GT given as G delta T or a sample. Let's not talk about the sample sequence right now. Now sampled version G delta T of GT can be written as G delta T equals GT PT. Fine. This is okay.
Yes, sir.
Equals GT summation n goes from minus infinity to infinity delta T minus NTS. Due to the shifting property of the Dirac delta function, I can equivalently write this as right.
Yes, sir.
Yes.
Yeah. Cool. So this process basically reduces the signal G delta T to a train of impulses whose amplitudes, now Because practically when we do this, we'll always have pulses with finite amplitude. We cannot have the delta functions practically, right?
Yes, sir.
So can be used what happened as a sequence for the samples of GT. Fine. So we get one condition that we can recover. This is how we get the samples of GT. We can convert GT from a signal to or a waveform to a sequence. Now we come to a second condition that, but we also wanted that GT should be recoverable from the samples Gn. So I say I define you get what I'm doing here, this equation, because this is slightly important to understand.
Yes, sir. You're basically taking the samples of G of t, right?
I'm taking the samples of g of t at time instant nts and mapping that to a discrete time sequence gn.
Time sequence. Yes,
Yeah,
sir.
so okay, so for signal systems you did follow this notation,
Yes, sir.
right? This is continuous
Yes,
time, this
sir.
is discrete time.
Yes, sir.
Yeah, so it's important to know how to go from one to the other. So we also wanted that GT should be recoverable from the samples GN. Fine.
Yes.
So, and I can write this G delta T as summation n goes from minus infinity to infinity Gn delta T minus NTS. So we'll come to the recovery process a bit later, but this is equivalent to fine. So since there is a one-to-one mapping between Gn and G delta T, Gt should also be recoverable from G. Fine.
Yes, sir.
Furthermore, since the Fourier transform signal is unique, Fourier transform of Gt should be recoverable from the Fourier transform of G delta t. Fine.
Yes, sir.
So we come to the Fourier transform of G delta t. So we know that GF is the Fourier transform and let G delta F equal Fourier transform of. Fine. Sorry, this is the wrong symbol. And but Fourier transform of GT PT, Fourier transform of GT convolved with Fourier transform of PT. Fine.
Yes, sir.
Yes, sir.
Now PT equals n equals minus infinity to infinity delta t minus nts. Fine. Or should I do the steps?
No, sir. It's fine.
Okay. Yeah, so the Fourier transform of train of pulses is another train of pulses, and the coefficients are given by 1 over Ts. This I can write Fs summation k goes from minus infinity to infinity delta F minus k Fs. Fine. Fs equals 1 upon Ts. So G delta F equals GF convolved with Fs times summation k goes from minus infinity to infinity delta F minus kfs. Fine. This beast equals Fs times summation k goes from minus infinity to infinity GF convolved with delta Fs equals Fs. So what is this convolution is, I believe, normal for you. I don't need to derive this
Yes, sir.
convolution, right? So
Yes, sir.
summation.
GF minus.
Huh. So this results in this results a periodic repetition of the spectrum GF. Fine. And so if I'm just drawing the amplitude spectrum because this is the best way to illustrate this. If this is GF, then say this goes from 0 to W. This is Fs. So there's another. So there'll be another copy of this around Fs. There'll be another copy around minus Fs. Fine. And the copies are inexact. But since you have already done sampling, you know that these copies will not overlap if the bandwidth of the signal W is by 2. Fine. This you know.
Yes, sir.
Yeah, and this,
Nyquist theorem.
yes, Fs equal to 2W for a band limited signal with bandwidth W known as the Nyquist rate for fine. This is known as Nyquist rate for the signal GT. Now, have you not done this in DSP?
So Nyquist rate.
No, yes, sampling.
Yes, sir. But
No,
not in detail, in brief.
okay, so bandpass sampling, has he covered?
No, sir, we already have sampled signals, right, in DSP.
No, DSP you have sampled signals, but some universities sampling and quantization is a part of the DSP course.
No, sir, we are more into dealing with filtering and design of filters.
Okay,
Uh,
that's what I call the boring part. I don't know how how are you guys being taught, but when I was taught DSP, this was the least interesting part. Possibly depends on the instructor. Yeah. Cool. So anyway, you know bandpass sampling. Okay, so have you not heard? You haven't heard of bandpass sampling?
No, sir.
Okay, so let's leave this for the next semester. Okay, so for this is slightly more involved. So for the digital communications course. Now, but now the question is derived Nyquist rate, but how do we recover GF from G delta F? So how do we recover GF from G delta F?
Sir, by applying a filter.
Yes, low pass filter. So
Pass filter.
GF is essentially a low pass signal. If we apply a filter with cutoff Fs by 2, then G hat F equals G HF equals fine. Fine.
Yes, sir.
And HF equals ideal filter. HT equals, this G hat is a bad notation, so let me call this G tilde because G hat I have already reserved for quantized signal. HT equals minus Fs 2 to Fs by 2 e to the power j 2 pi Ft df equals Fs j pi Fs t minus j pi Fs by pi, right, equals Fs sine right. Fine.
Yes, sir.
Yes, sir.
Great. So G tilde T equals G delta T convolved with Fs sync Fst. Fine. Equals summation n goes from minus infinity to infinity Gn delta T minus convolved with Fs sync. Sorry, no, this is not Gt, this is Gn. Fs sync Fst equals summation n goes from minus infinity to infinity Gn Fs outside sync T minus, sorry, Fs T minus. Fine.
Yes, sir.
So now basically if you satisfy the Nyquist sampling theorem, you can interpolate GT from its samples and sync Fst fine. So you know that the sync function is called the interpolation function.
I don't remember exactly, but yeah, now we got to know. Like,
Okay, cool. Which is a good thing. We learned something new. And do you know sync? Did you know this?
No, sir.
Okay, you can find this, means you can show this, but the important property here is at t equals NTS sync t minus MTS equals 0 for all m not equal to n. This you know. This you would know. Oh, sorry. Sync fs. There should be an fs here. So I'll just fs t minus nts. NTS.
So your second statement is basically finding out the zero crossings of the sink, right?
Yes. Fs zero crossings, and the important property that if you look at this function, so at t equals NTS, this will be 1, and the contribution of all the other GMs. So GM m not equal to n at time instant n will not contribute to GT at all. That's the main point. That at the fixed time, at the given time instant, only that sample will count. And between two samples, it will be the linear combination of multiple samples. Weighted by this sync function. That is the key idea here. You follow that?
What will not contribute to GT?
So at say, if I look at, say, I look at, so I have GT equals summation n goes from minus infinity to infinity gn sync of fs t minus I have this, fine. Now
Yes, sir.
at t equals kts sync fs t minus mts equal to 0 m not equal to k, fine.
Yes, sir. Sir, actually, in above at t is equal to MTS should have been written. Like that's why we got confused, I guess.
Oh, sorry. So now is it okay?
Yeah. At
Yeah, so
NTS it is 1, I guess. Yeah. Okay, fine.
yeah. So that is basically, that's the property of sin pi t over pi t.
Okay, sir.
Okay, and you can actually view the delta function as a limiting case of the sync function as well. Okay, if you look at it carefully enough. So now based on this, so this is the basic discussion on sampling, but have we cannot practically Dirac. We can practically have the Dirac delta function, right? We have to have certain limited pulses, or we have to have realizable pulses. So consider practical PT equals summation k equal to minus infinity to infinity d t minus nts, where dt equals 1 minus delta by 2 to, or minus delta by 2 less than equal to t less than t, and fine. This is a practically realizable system.
T less than
Less
delta
than
by
delta
2.
by
Oh, sorry,
2.
sorry. Delta by 2. So this is a practically realizable system.
Yes.
Yes, sir.
Yes. So basically what you are doing here is, suppose this is your, sorry, yeah. So let
Shouldn't it be 1 by delta
what?
or only 1? Because
You can have it 1.
okay.
We are not approximating the delta function.
So
It is
won't the
not.
integral be changed, like if we don't
Yeah.
take the area as 1?
Yes. That is, you will see that effect as well.
Okay.
Okay, you can work this out for 1 over delta as well. That won't make life too hard, but that's not the effect that we are trying to look at here. There is some other effect that we are trying to look at, and possibly we'll have to postpone that to the next class. So this is, say, GT. This is the signal GT, fine. And sample it using DT. So 0. Now delta is an extremely small width. So this is the sample that so the red markings on this line are the samples that you will be able to collect practically, right?
So just one thing, practically collecting in a sense, like there would be a signal, and at time instance, like if we write a code for this, like for
No,
collecting
not a
the
code,
sample.
Code is a
Okay.
gross misrepresentation of things here.
Okay. So everything we are dealing with formulas itself. Okay.
No, we talk about a practical electrical system,
Okay.
because code you can idealize a lot of things.
Okay.
Here
Okay. So
what we are
got it.
talking about, that we are generating a finite width pulse. We'll have to
Okay.
multiply it with a finite width pulse. So
Okay.
did anyone look at AD633?
Sir,
I told you to do this in AM.
Sir, multiplier, right?
Yes, AD633 is a multiplier. And so you can sample using the multiplier, and basically you will be multiplying something like a rectangular wave with the signal of interest.
Okay.
A rectangular wave is an extremely small duty cycle with the signal of interest.
Okay.
Right? This is called, since this form of sampling is called natural sampling. And for this, we will again first require the Fourier series coefficients of PT. Okay, because again, G dt, oh sorry, G dt equals GT PT and GDF equals GF PF. Now the good thing is that this PF will be, oh sorry, convolution this, but at the same time, this PT, if I look at it, PT is basically convolved with fine. Or PF will be DF Oh, one node crashed and it's time. So I believe we'll stop here and continue on Monday. Oh, sorry, continue on Tuesday then.
Okay, sir.
Yes, sir.
Great. So I'll disconnect this meeting and we'll continue on Tuesday.